Hi, my name is Parth Parak. I am a fourth year computer science student at The Ohio State University. For the 2020 to 2021 competition season, I was the vice president of the team, and for the 2021 to 2022 competition season, I will be the president of the team.
Hello, my name is Blaine Miller, and I'm a newly graduated senior from The Ohio State University with a degree in computer engineering. I've been on this team for 4 years, and I've been to 2 competitions.
Hi, my name is Hayden Gray. I'm a sophomore and I'm studying computer science here at The Ohio State University, and I'm a member of the software team.
Hi, I'm Mitchell Sayre. I'm a junior at Ohio State studying computer science, and I'll be the software team lead for the 2021-2022 competition season.
Our current team roster is completely composed of undergraduate students, with a lot of us being freshmen. This is why we put a hard emphasis on making sure that we have readable and teachable code for everybody that is new to the team. We try to make sure that people can get on the team and start working with our sensors as easily and as quickly as possible. Sensor optimization is really important to us. For us, it means reducing uncertainty of where we are versus where we think objects are. We try to use sensor optimization in many different systems in our robot, and making sure that all of our sensors are completely optimized and we're the most certain about all of our inputs, make sure that we can be successful in competition.
A large chunk of our sensor optimization happens in the localization system. The localization system is where we use an extended Kalman filter, or EKF, to estimate the current state of the vehicle from our many uncertain sensors. By state, I mean the position, orientation, velocities, and accelerations of the vehicle. The way that it works is the EKF constantly has a current estimate of the state of the vehicle. It will then receive uncertain measurements from the sensors, and every time it receives an uncertain measurement, it will consolidate that with our current estimate of our state to come up with a better estimate of our state. Here's our 15-dimension state vector that we use in our code. Each of our sensors provide us a little bit of information about different parts of the state vector. The 3 sensors that we use are an IMU, DVL, and a depth sensor. Our IMU is our most accurate sensor, and it provides us information about our linear acceleration, orientation, and angular velocity. Our DVL provides us information about our z, y, and x linear velocity, and then finally, our depth sensor provides us information about our z position, which is how far away we are from the surface of the water, but knows nothing about our x or y position. As you can see, we have no sensor that estimates the x or y position of the vehicle. The way that the EKF handles the estimation of these parameters is by integrating velocity over time. This results in a very uncertain metric of how far the robot has traveled that gets more and more uncertain over time. In the same way that we incorporated sensor measurements earlier into the EKF, we can incorporate any estimate of state, whether or not directly from a sensor. The goal of the rest of our sensor optimization system is to provide an estimate of the x and y position to feed back into localization.
The team has implemented an entirely new approach to how a robot will perceive objects. While many modern vision systems simply detect where an object is located in the camera viewport, we determined that an entirely new solution would improve our ability to detect objects and increase how certain we are of our robot's current state. We trained our new perception system to estimate an object's true position and orientation in the world relative to our robot. And with this model, we now have real-time estimates for true x, y, and z, as well as roll, pitch, and yaw of all game objects we have trained to detect, supplying us with much more information than the traditional approach of object detection. For teaching our model to make these estimates, we needed a way to extract an object's true position and orientation in every frame of the training set. In under 2 hours. We then applied aggressive data augmentations for every frame in each training iteration to ensure our model could identify the object we trained on in any condition.
A new system that the team has developed is a 3D mapping system that keeps track of objects of interest in the environment and also relies heavily on the previously mentioned perception system. Mapping works by listening to anytime perception detects an object, and when the object has been detected, mapping will report its position, orientation, and covariance. Mapping does this every single time an object is detected. However, this new data does not simply overwrite the old data that we already have. You see, since an object may be detected hundreds or thousands of times in any given session, we don't just want to overwrite the old data. We can actually use that fact to our advantage to create an even more accurate estimate. This works by taking the covariance of the new and old estimates and combining them in such a way that we get a more accurate estimate. Mapping also conveniently allows us to localize the robot's position and orientation, as well as all the objects it's keeping track of. You see, since mapping has to know where all the objects are in the world with relation to the robot, it also has to know where the robot is with relation to those objects. This gives it the ability to not only figure out where important tasks and obstacles are, but also give our localization system clues as to where it is.
All of these elements combine to help us complete our tasks and competition. We ingest all of this data in hopes that once we filter through it, we can take that data and derive emergent behaviors from it. One of the most important things that our robot can do is search. Having optimized sensors and all of these other systems that go along with having optimized sensors allows us to complete a search finally. Two big things that you need when you search is an idea of how certain you are of where you are, so where you have searched, as well as how certain you are of where the object you're searching for is, so your search area. Having optimized sensors along with this system allows us to have those two things and have a very successful search algorithm. Another big thing that our robot can do now is navigation from point to point in the pool. In the past, what we would have to do is guess which direction we would go after we're completing an obstacle in the course. Now we have a way of mapping the course and being able to search an area, and having these other systems allows us to go from point to point within the pool because we have a rough idea of where things are. Another really big thing is being able to do some of the tasks, like being able to confirm that we shot a torpedo through the torpedo target, because we can get more and more certain about where those things are in the pool. Importantly, sensor optimization really leads us to be less uncertain about things around us in the environment, and we can derive all of that data and use it for things like task code, navigation, mapping, and all of our competition tasks.
The main tool that has allowed us to continue development during the pandemic is our simulator. Our simulator, Gazebo, is a program that simulates the thrusters, physics, and sensors of our vehicle. This enables us to test our code and make sure that it behaves properly without renting a pool. It does not completely eliminate the need for in-water testing, but it does enable us to have more bug-free pool tests. The first system that we implemented was localization. We found a ROS package named Robot Localization that did exactly what we wanted. After simulating our sensor noise, we started up the EKF and could view our estimated state. As you can see, the estimate is stable, but as the large purple circle of uncertainty demonstrates, we are not very certain about our X or Y position. After getting it running in the simulator, we ran it in the real world. Again, the estimate was accurate, stable, responsive, but still not very sure of X or Y position.
As we developed the perception system, we used footage from the simulator extensively. This footage served as a benchmark for when we were on the right track with our training. When we had successfully trained our model to detect objects in the simulator, we applied extensive data augmentation so our model would succeed in even the most poor visual conditions, including those observed underwater. Once our model succeeded with all the real-world footage we had to show it, we integrated it into our robot system fully and tested it live. Observing successful detection, our model had achieved a general fit, meaning it succeeded in many environments with drastically different conditions.
Our mapping system was tested extensively using Gazebo and RViz. It's also important to note that since perception and mapping were built alongside each other, and since mapping is dependent on perception, we use a boiled-down version of our perception system to test mapping iteratively. When testing, we focused on two things: the accuracy of the pose data that we were getting from each object, as well as how confident the system was of that data.
When we tested the task code and navigation for our robot, we tried to use all of our different tools, the simulator, pool tests, and many more different tests to try to get the robot to generate trajectories. During a pull test, we're able to give the robot commands and have it go from point to point and generate those trajectories from where it thought the bounds of the pool were to where we thought the robot should go from point to point, which is really good. Another thing that we were able to do is test it with obstacles in the simulator, which is really important because we're now able to generate trajectories due to all of our sensor optimization and our techniques of smoothing out our sensor data, and show that we can avoid objects or we can go directly to objects even if we only know a guess of where it is.